Yeah, so we continue here. Yeah, so A and KT, I can now write it as A and KT is equal to integral phi n star psi kt d2. Right, this is a way to express the value of A and KT. So what is phi n star? Phi n star is the complex conjugate. Complex conjugate of the of phi n my orthonormal function, and what is d2? d2 is the volume element in the coordinate space. Right, we have moved forward from the phase space to the coordinate space now. So that is it. And now I can try to manage it with the IH cut. Right. So IH cut NGT is equal to IH cut phi n star psi kt. No, it's all getting wrong. Sorry for that. Okay. So we have this expression for this one on there. So let's do IH cut NKT dot is equal to IH cut integral. We use this function, right? Phi n star psi k dot t d2. Now I can, let me put this as equation 3. I can always substitute from the equation 1. This is the equation 1, and we will apply that over to this expression. So while I apply that, I can write this as phi n star h of psi kt d2. Right, because psi k dot t is equal to h by IH cut psi kt. IH cut got cancelled, and therefore I got this expression. Now I can always express this psi kt in terms of the orthonormal function phi n, which I earlier wrote it as equation 2. So let's do that. Integral phi n star h small m phi m d2. Right, here substitute equation 2 into this one over here, and that I can write it as the sum or nm h nm amkt mkt, right, where h of nm is equal to integral phi n star h phi m d2. Right, So that is it. And I know that if I need to talk about ANKT, sum over ANKT squared is equal to 1 for all k in our case, right? We have made this statement in the beginning also, because when we define the ANKT, we define that probability and the corresponding expressions. So therefore, sum over n ANKT squared is equal to 1. Right? We have already taught. I have already discussed this in the beginning. So this summation over the probability has to appear definitely 1, because ANKT squared represents a probability, and summation of the probability must sound to 1. Now we will introduce something called the density operator. Density operator, let's name it as rho t. And this density operator is defined by some matrix elements which in general are represented by rho m and t, right? So there is a density operator rho t, and it is a matrix, and its elements are represented in general by rho m and t. And I can write information on rho m and t as equal to 1 by script n sum over k equal to 1 to script n AMKT ANK star t, right? Right. So what does this equation tell you about the matrix elements? Basically, this density, the matrix element rho m and t is the ensemble average, right? This is what? Script n. Script n is the total number of elements in the ensemble. So it is the ensemble average of some quantity AMKT into ANK star t. So that is it. So the diagonal element in this situation, which is rho n n. So rho n n will basically give me the ensemble average of the probability a and t square, right? Basically, it's a case of a double averaging, right? So the diagonal element rho n and t is the ensemble average of the probability a and t square, right? So that is it. So that much about the discussion, and the carryover from this equation is that we know there is something called a density. We have introduced something called a density operator, and we have defined the elements in the density operator by the notation rho m and t, and this is how this matrix elements will look like. We will see the significance of this density operator and all those things in the coming videos. This is going to be a central part of our discussion on the whole quantum statistics. Yeah, so all this all this previous discussion was just to make a ground for introduction of this rho m and t, so that you know what does an AMKT and the NK star, from where it comes up. So that is it. So we will continue in the next video with more discussions on this matrix elements and its characteristics. Okay.